I'll have it like this.
All right, so welcome. We have a couple maybe joining us here in a minute, but we're going to get started. Yeah. Let's see. All right, so just kind of an agenda for the day. If you took your 11B test and were not happy with your score, again, make sure you talk to me about that, and we can set up a retake. If you haven't taken it, you need to get that done. Today, we're going to talk a little bit more about probability events, some basic probability. Yes, there is a new packet. Yes, it is in the office. Yes, it is also in the Schoology page. So I will show you that, where you can find it. Maybe. No, that's not right. All right, so if you go to the third hour page, chapter 12 is where we're at. And there is the note packet. It is possible, if you're using a school computer, that you can actually open this through Kami and write on it and save it rather than doing it on paper. I just don't know how easy that is to access then as you do tests and quizzes, things like that. And then you can see the day 2 stuff is there, ready to go as far as assignments for when we're done with notes. All right. Item number 2. Actually, item number 3. You'll have some work time when we're done. you will have a warm-up, a note check, and homework to do, all on basic probability. Homework is on Schoology, as you just saw. And if you haven't done the first day, that's where I would start. Day 2 is going to be just a lot of the same, just taking it one step further. And then a reminder, missing work is due by Wednesday, November 4th. So after November 4th, all of the Chapter 11B homework will no longer be accessible. You won't be able to make that up. All right? Questions? Again, you can always feel free to send questions through the chat. It is set so that I am the only one that can see it. I'm not sure. I've got the chat open now. Can anyone see that it's open? All right. So this is what your warm-up will look like. And again, it is typed up on the Schoology page as well. 2 questions, just finding some probabilities. Assume that after question 1, you find that probability. You're back to 40 marbles with 8 being green and 2 being blue for problem number 2 as well. All right. So probability events today. On Monday, we talked about mutually exclusive events being 2 events that cannot happen at the same, if one event happens, the other one cannot. Today, we're going to go forward with things like independent events and dependent events. So if we have 2 events that are not mutually exclusive, so both events could happen, then the probability that A happens or B happens is the probability that A happens plus the probability that B happens minus the probability that both of them, A and B, happen. So if we look at this Venn diagram, what this is saying is we take, so the probability that either A or B happens, well, we get all of this, and we get all of this. But the problem is, then we've counted this part twice. So we need to remove one of the countings of A, B, both A and B happening. All right. Moving on. All right, so in a certain class, there are 32 students. 7 are in AVID, and 10 are athletes. 4 of the students are both AVID students and athletes. find the probability that a student is an athlete or an avid student. So in order to do this, I need to know how many students are in the class. You can certainly unmute and shout it out or use the chat, but how many students are in this class that we're talking about an example?
32.
32. Excellent. That's going to be my denominator. How many students are athletes?
10.
10. So my formula says take the, actually, if I follow the formula exactly, we would go 10 over 32. How many are avid students?
7.
7. Excellent. So that's the probability of athletes plus the probability of avid students. And now I need to subtract the probability that they're both. So how many students are both avid students and athletes?
4.
4. Sorry, I had to plug in. I'm running out of power. So I subtract 4 out of 32. Come on. There we go. So let's see, if I took my shoes off, I could do that adding with my fingers and my toes. I'm gonna, hopefully I don't need to do that. What is 10 plus 7?
17.
17. And what is 17 minus 4? Excuse me.
13.
13. Excellent. And I can do that because my denominator is the same for all three fractions, 32. The next thing I should do, the last thing I should do, can I reduce that? Is there a number other than 1 and -1 that divides evenly into 13 and 32?
No.
No. So I cannot reduce. This would be my answer in fraction form. You certainly could choose to write it as a decimal or as a percentage. But seeing it, I mean, it worked out so well in fraction form, I would probably leave it that way. All right. Then what is the probability that a student is neither an avid student, and that I think should be a nor an athlete. So the probability that not avid and it says or, so let's go and or not athlete. May need that information again. So same class, so we still have 32 students. How many are not in Avid?
Uh, 25.
Great, how did you get that?
I just subtracted the 7 students that were in Avid
Perfect,
out of the 32 that were in the class.
yeah. So if 7 are, that would mean 25 are not, just subtracting. Excellent job. And then how many are not athletes?
$22.
22. And then we have to subtract off the ones that we double counted. So how many are not athletes and not Avid students?
$28.
28, yep. So same thing, subtracting the 4 that are both from the 32 gives us 28. Okay, and then if we add, so 32 is going to be our denominator. If we take 25 plus 22 minus 28, I think we get 19. Okay. And then again, we should check, can we reduce? Or is 19 over 32 in as reduced as that fraction gets? $19 is a prime number, so that's set. I'll show you at the end, there's kind of a nice way if you have a graphing calculator, or if you're using one of the graphing calculators, to have it reduce a fraction for you. Right? Questions on that one? The other way you could have done part B is you could have taken 1 minus your answer in part A. So 32 over 32 minus 13 over 32 would give you that 19 over 32. So several different ways to get that correct answer. All right. A couple for you to try, 3 for you to try. And what I'm going to do is go to a full screen so that all of them can be visible, I hope. All right, yep, there we go. And there. So, and I'm going to have you work on these. A shoe store made 51 sales today. 13 customers bought boots, 17 bought work shoes, and 5 bought both boots and work shoes. So what is the probability that someone bought work shoes what is the probability that someone bought work shoes or boots? And what is the probability that someone bought neither work shoes or boots? All right, so I'm going to give you a little bit of time, maybe we'll check back in a minute and see where you're at. I muted myself, sorry. But I'm going to mute and stop my video, and we'll be back in 1 minute. All right, and I'm back. So what is the probability that someone went in and bought work shoes? Again, you can either unmute and just shout it out or put it in the chat.
13 out of 51.
Say that again, Henry, because I think I misheard you.
13 out of 50, 13 51s
How,
by decimal
where did
fraction.
you get the 13 from?
Like 13 customers brought boots.
There you go. Excellent. 13 out of the 51 total. Can I reduce? That 51 looks bad. I'm gonna. Can I reduce that? Is there a number other than one that divides?
No.
Yeah, nope. 13's called a prime number. Only divisible by 1 and 13. 57 has some numbers that divide into it, but 13 isn't one of them. All right. The probability that they bought work shoes or boots.
Would it be 25 over 51?
Yeah, excellent.
30 over
Back to
50.
number one for just a second, but so let's if we write this out, it's going to be 13 over 51 plus 17 over 51 minus 5 over 51. And if you take 13 plus 17 minus 5, that is 25. And my denominator is 51. I want to go back to number one because I think what we found in number one is the probability that they bought boots instead of work shoes. Because 13 bought boots, but we wanted work shoes. So I think 17 out of 51 bought work shoes. And that does reduce. 17 actually divides into both. Gives me 1/3, okay? So the 13, it just was the number that bought boots and not the number that bought work shoes. That's why that's not 13 over 51. All right, then the last question. What is the probability that they bought neither boots or work shoes? Work shoes or boots? I think anytime you get that neither, the easiest, if you've already calculated the probability that they bought one or the other, the easiest way to do that is going to be take everything minus the probability that did buy work shoes or boots. And then we should see if that reduces. I don't think it does. We can double check that later. All right. So that's events that are not mutually exclusive. So one type or two types of events that aren't necessarily mutually exclusive are independent events and dependent events. So events are independent if and only if, which means they're independent if one event happening does not affect the probability of another event happening. So if you know they're independent, you know that the probabilities don't affect one another. If you know the probabilities don't affect one another, you know that they're independent. It works both ways. An example of events that are independent. Flipping a coin and rolling a die. So getting heads rolling a die and getting 3. Doesn't matter what I flip on the coin, the probability of rolling a die and getting a 3 is just going to be 1 out of 6. Events are dependent if one event happening does affect the probability of another event happening. So maybe rolling a die and getting a 3. And rolling 2 dice and getting a total of 9. So if I roll 1 die and I get a 3, and then I roll a second die, getting that 3 affects the probability that I'll get a total of 9. So those are dependent. And a lot of times dependent events have to do with doing the same type of thing twice. Doesn't work for coins. Flipping a coin and then flipping another coin, those are independent. So flipping a coin and getting heads and flipping a second coin and getting heads are independent events. But rolling 2 dice, getting a certain number on one and a sum of a certain sum on the other are dependent. All right. So determining whether we have independent or dependent events. So, oh boy. So our question is, a jar contains 12 green marbles and 8 violet marbles. A marble is chosen at random from the jar. You look at it, memorize the color, put it back, and mix them up, and then draw another marble from the same jar. Does the color of the first marble chosen affect the possible outcome for the second marble? So in other words, are they independent? They're independent if the probabilities are not affected, or are they dependent? And if I can do this, I'll have it as a poll. So go ahead and vote. Is it dependent or independent? Does what I draw on that first draw affect the probability of my second draw? It's a tight race. Got 4 more people we're waiting on. Three more. One more. Uh-oh. Five seconds left. 4, 3, 2, 1. All right. So let's talk about this. What is the probability that I draw a violet marble? Just shout it on out. It doesn't even have to be a reduced fraction. Caden, are you, you're muted, but if you unmute, you can certainly give an answer. All right, what do you get?
Hello.
What's that?
I couldn't hear the question. What was the question again?
Oh, certainly. So how many, what is the probability that you reach in the jar and get a violet marble?
The probability would be one in I'm trying to think.
So how many violet marbles are there?
8.
8. How many total marbles?
The probability would be 2/3. Wait, no.
You are on the right track. I think I know what you did. Did you do 8 over 12?
Yeah.
Yep. So, but it should be 8 over 20. So just, or 8 over, yeah, 20. You should just add the two together.
2/5.
Yeah, yeah. Okay, so 2/5 to get a violet marble. Then I'm gonna put that marble back. So how many violet marbles are in the jar this time?
8.
Yep, still 8. So did it change will the probability change?
No.
No, so this is independent. Easy for me to write. There we go. They are independent. All right. How about this one? And I'll launch the poll again. Relaunch. And okay. So now a marble is chosen at random and it is not replaced. So we reach in, we grab a marble, we look at it, we put it in our pocket, and then we reach in and grab another marble. Are they dependent or independent? Does the color of the first marble affect the possible outcomes for the second marble? If it does, dependent. If it doesn't, independent. All right, got a little over half. Oh, a lot over half now. Excellent. A couple more people. 3 more folks to join the poll. All right, 2 more folks. And 5 more seconds. 5, 4, 3, 2, 1. All right, ending polling. Yeah, by far we got on that one that those are dependent. And one way to think about that, if I have 20 marbles in that jar and I draw one out, now I only have 19. So my probability, the denominator in my probability is going to change. So if the denominator changes, almost always the overall probability is going to change. That is dependent when we did not replace it. All right. So if we have events that are independent and we want to know the probability that both happen, both A and B happen, we take the probability that A happens times the probability that B happens. Whoa, that's a bad B, Mr. Gingrich. Here we go. And that only works if they're independent events. So a couple of things that you might notice when we talk about events that are mutually exclusive, almost always we talk about or, because if we say and, then the probability is 0. And when we talk about independent events, we use and a lot. All right, moving on to a couple of examples. Alex cannot decide which shirt to wear today, so he chooses one at random. He has 2 yellow shirts, a green shirt, and a purple shirt. The probability that it rains today is 40% or 2/5. What is the probability that Alex chooses a yellow shirt and it does not rain today? So the first question we should ask is, are these independent events? Does the color of Alex's shirt determine whether or not it's going to rain?
It's independent.
Yeah, they're independent. Excellent. So what is the probability that he just randomly grabs a shirt and it's yellow?
One over 2.
Ooh, not, oh yeah. Okay. You reduced it. That's awesome. 1 over 2. And what is the probability that it rains, that it does not rain? Sorry, does not rain.
3/5.
3/5. Excellent. And when we multiply fractions, that's the easy one. We just multiply straight across. So we get 3 over 10. Again, you could write that if you wanted as a percent. You could leave it as a fraction. So it'd be 30%. You could write it as a decimal, 0.3. Any of those, they all mean the same thing, and all of them are correct. Okay? So a couple of things with fractions to decimals. If you take the numerator the fraction bar is just like saying divided by. So this would be 3 divided by 10, and it would come out as 0.3. All right. So the second one, find the probability that Alex chooses a green shirt and it does rain. So I'll go back up just for a moment here. Actually, let me do this. So what is the probability that Alex chooses a green shirt?
The probability that he chooses a green shirt is 1/4, and the
1/4.
probability that it rains is 2/5.
Okay,
So you would multiply across and get 2/20. Then that would go down to 1/10.
excellent. Exactly right, perfect. And again, you could write that as, that would be 10% or 0.1 if you prefer decimals or percentages. But I like it, again, it works out really nice as a fraction. All right. A couple to try on your own. Aaron believes that there is a 60% chance his bus drops him off at home on time, and a 30% chance that his mom makes pasta for dinner tonight. Are those dependent or independent?
Independent.
Independent, correct. One does not affect the probability of the other. So what is the probability Aaron gets home on time and his mom makes something other than pasta? His mom does not make pasta for dinner. And then what is the probability Aaron gets home late and his mom does make pasta? I'm going to give you a minute and a half maybe, and then we'll come back and talk about them. All right. So what is the probability that Aaron gets home on time and that his mom makes something other than pasta?
The 60% chance that the bus drops him off on time is 3/5, and then the 70% chance that his mom makes something other than pasta for dinner is 7/10. So when you multiply across, you get 21 over 50, and then you can't simplify that.
Excellent. So there would be as a fraction. In this case, they're given as percentages, and percentages don't multiply real well. You could convert it to a decimal and do 0.6 for 60% and 0.7 as the 70%. And you get 0.42. That would work out. And then if you wanted, you could make it 42%. So a couple of different ways to do that, whichever you're more comfortable with. All right, what is the probability that Aaron gets home late and his mom makes pasta for dinner?
The 40% chance that he gets home late
Okay,
is 2/5, and then the 30% chance that his mom makes pasta for dinner is 3/10. So when you multiply it across, you get 6/50.
2/5, 3/10, 6/50. Whoops. And then can I reduce that?
Yes, you can reduce it. You can reduce it to 3 out of 25.
There you go. So again, that's reduced. If you prefer doing it as decimals, you could do the 0.4 times 0.3, and that is 0.12. As a percentage, that would be 12%. All of those would be correct. Now, a couple of things that we really haven't talked about is values for probabilities. Every probability has to be between 0 and 1. So if you're doing probabilities and you get an answer that's larger than 1, you probably did something incorrectly. And that really can happen when you're working with percentages, if you're not careful on how you deal with them. All right, we're going to draw some cards next. Cards are drawn at random from a standard deck of 52 cards and they're replaced. So you can draw a card and put it back. What is the probability that you draw a red card and then you draw a 7? So probability of red and then a 7. So what is the probability that you draw a red card?
The probability that you draw a red card is 1/2, because half the cards are red.
Exactly. Good.
And then
Just a second, Caden, and I didn't mean to cut you off, but we're not talking about jokers. We don't have any of those. So 1 out of 2 for red And then Caden, go ahead. You were going to finish that up, I think.
There's 4 over 52 sevens, and then you can simplify that. Wait, can you simplify? I don't think you can simplify that. Never mind.
Nope, you can. You were right. You
Oh,
can.
you can.
Yep. 4 actually divides into both, and it gives you 1 over 13. Because if you think about it, each suit has 13 cards in it, and one of each of those cards from each suit is a 7. So good job on getting that. I mean, perfect. Now the hard part, 1 times 1.
It's 1 times 1 equals 1, and then 2 times 13 equals 26.
There you go. 1 over 26 is a good answer. All right. What is the probability that you draw an ace and then without replacing, so you draw your ace and you have it, and then without putting that card back, you draw a face card. I think we can use a little bit of Caden's results from the last example. The probability of drawing an ace, 4 out of 52, which reduces to 1 over 13. Now, I took that one out.
And then
Go ahead.
the chance that you draw a face card is 12 out of 52, because there's, of course, 12 out of 52 cards. And then I'm pretty sure you can also simplify that down to 3 over 13.
You are close. But because I didn't put the ace back, I don't have 52 cards left in the deck.
Oh, you didn't replace them. Okay.
Right.
And
So then I only have 51
took out
cards.
the 4.
Yeah. Yeah.
So
Otherwise,
then it's 3 out of 12
for what?
for like the simplification of 12 over. Wait, never mind.
Okay. Okay. And then we multiply across. 13 times 51 would be 510 plus 153. I think I've got that right. I'm gonna double check that just because I don't want. Yeah, 663. All right. And then can we reduce? And in this case, we can. There's a 3 that factors out of there. It gives us 4 over 221. All right. Probability you draw the 3 of hearts. And then without replacing, you draw a queen. So what's the probability of the 3 of hearts?
One over 52.
1 over 52. There's only one 3 of hearts in the deck. Ooh. See if I can get my 2 a little bit better. And then I don't put that card back. So how many cards are left after I draw the 3 of hearts?
51.
51. And what's the probability? How many queens are in the deck?
4.
4. Multiplying across, we get 4 over 26, 52. And we should know that that's going to reduce because they're both even, the numerator and the denominator. And actually, they're both divisible by 4. 1 over 6, 6, 3. So one of the things with cards is when you're doing multiple draws, your fractions tend to get pretty large denominators. So last one on the card examples. Now we're going to draw 3 cards and we're going to put it back after each draw. So what is the probability that you draw a 9? Then a card that is black. Then a face card. All right, so what is the probability? How many 9s are there in the deck? Or what is the probability of drawing a 9?
4 over 52.
4 over 52. And then I draw that 9, I put it back in the deck. What is the probability that I draw a card that is black on my next draw?
1/2.
1/2. I draw that card, I look at it, I put it back in the deck. And what is the probability that on my next draw, I draw a face card?
Twelve over 52.
Yeah, 12 over 52. Well, this will be a good one to use calculator on. So what I'm going to do is pull up my calculator and I'll show you one of the nice features of the Texas Instruments calculators. Also, possible to use with Desmos. It's just a little bit different. So if I share my screen. So we took 4/52 times 1/2 times 12/52. And if I just hit enter, I'm going to get a decimal answer. Okay. But it would be nice because we had those fractions. It would be nice to have it as a fraction. So the way you do that on your calculator is you use this button called math. And you hit math and then you press enter twice. So this is 0.0088757396 and so on is actually the exact same as 3/338. A lot of threes there. So that, again, that process, I did math and then I pressed enter twice to get it as a fraction. All right. Go ahead and try these two. Again, I'm going to give you about a minute. We have a jar with 12 green marbles and 8 purple marbles. What is the probability you draw green, replace it, draw another green? What is the probability you draw purple? Then without replacing it, so you keep that purple one out, then you draw green. All right. Probability of green and then green. How many green marbles? Excuse me.
There's 12 green marbles
How many total marbles?
over 20.
All right. And then I see that it's green, I put it back in the jar, mix them up, and I draw another one. So what's the probability that that second one I draw is green?
There's still 12, so it'll still be 12 over 20.
Yeah. So I actually like, Caden, what you had done earlier is you reduced right away, and it actually makes the problem a little bit easier to work with. You don't have to, but this would be 144 over 400. And so again, I could just go back to my calculator and let my calculator help me out a little bit. 144 divided by 400 and turn it into a fraction. Nine over 25. All right, what is the probability that we draw a purple marble on our first draw?
There'll be 8 over 20.
Yep, excellent. And what's the problem? Now I draw that purple marble out, I put it in my pocket. Now, what's the probability I draw a green marble?
It'll be 12 over 19.
Yeah, good. Be even better if Mr. Gingrich could write a 12 on his computer here. There we go. And again, I would use my tools to help me with this one a little bit. We had what, 8 over 20 times 12 over 19 and turn it into a fraction. 24 over 95. All right. I looked at the clock and I went longer than I wanted to today, but very good class. I'm very happy with your efforts today. I am going to turn off the recording.